Alright guys, welcome to episode 2 of the car physics tutorial. In this episode there's no preview, as you can see, of what we're going to make because this is not so much forces or physics related. This is more like a stepping stone to the future basically. And what we're going to be talking about today specifically is steering, and more importantly, more realistically, we're going to talk about Ackermann steering. So the way it works in a car, and I have a pretty picture. Let's just ignore the text for now. I'll explain it in a bit. So in a car you have the front wheels that obviously, if you steer, will either turn right or left depending on which side you're turning the steering wheel into. But the thing about that is, if the wheels themselves would just be the same angle, this would actually cause issues for the car, especially at higher speeds. Because the turning circle basically would be different for both wheels if both of them were the same angle. So currently you can see that this one, this is the center of the turning circle, so every car has its own turning circle, which is roughly around 10 to 12 usually, but you can find that out. That stuff is online. But as you can see in this example specifically, because this is how Ackermann steering does it, both originate from the turning circle center. So imagine like a circle around this center, which this actually, as you can see, is the turning radius. So from the center of the car to the center of the turning circle is the turn radius of the car. But in this example that I drew up here, both of them go to that center of the turning circle. Now, if we would have the front wheel, the front right wheel in this case, the same angle as this wheel, then obviously this line, let's see if I can find it in my list layers. Always name your layers. So this line would then be, let me just, there we go, and then just remove this part because otherwise we're taking that with us. So then this would be right here, and as you can see, the turning circle would be around here for the other wheel, which is not correct because that's not how a car steers, because that would actually clash with this left wheel, and this left wheel would actually start slipping, which creates less traction. And on that note, also make sure that you can't steer as well. So what Ackermann steering does is it takes the angle from the center of the turning circle and applies that to both wheels. So in this case, the right wheel, because we're turning right, is angled more basically than the left wheel. And if we would turn left, then the left wheel obviously would be turned more than the right wheel, because then this center of turning circle would be on this side of the car. So then the angle would obviously be different. Now, how do we calculate this? And this is actually a four-way calculation basically, because we need to calculate it for both turning right and turning left. And let's just ignore the RAD2DEC for now, but basically we need to get an A10 calculation, because it is sort of like a Pythagoras statement. And we can use the wheelbase in meters, which in this case would be from here to here, which makes this a straight triangle, as it's called. So that's why we can use A10. So we need to wheelbase in meters, and we need to divide that by the turn radius in meters, so which is this line, plus or minus depending on which wheel, and that's why I added it here. So plus the rear track in meters, so this entire length, divided by 2, because we only need one side of this, either this side or this side. So in this case, in the terms of the left wheel, we need to add the rear track. So this half area, this half portion of the rear track, we need to add that to the turn radius. Or in the case of the right wheel, since we're turning right, we need to take the rear track half off the turn radius, so that the calculation will be done from here. And then, of course, we need the steer input, because without the steer input, it's going to turn on its own, which is not something that we want. Now, since in Unity, I don't know if this is actually true for real life, but in Unity, if you perform a mathf.atan or mathf.syn or whichever, I don't know the name actually for that. That is terrible. I've been out of school for like 11 years, so you know I'm old. Come on, give me a break. No, but anyways, any one of those tan, cos, atan, sin, you know, any acos, atan, asyn as well. But any of those gets an output value in radians, and since we want it in degrees, because that's the actual angle eventually, we need to actually multiply by rad2deg. That's the only reason why this is here. So you don't need to really worry about it. It's just because this mathf.atan calculation will actually give you a radians as an answer. We need rad2deg to fix that basically, because radian to degree, that's what it stands for, which is what I also posted here. So we need a view values. So in this case, we need the turn radius in meters, which is the radius of the circle of turning. But like I said, that is something that you can find online generally. Then we need the wheelbase, which is also something that we can find online. And lastly, we need the rear track, also in meters. So all three in meters. And then within Unity, we can obviously set the steer input. And Unity also has the rad2deg, so we don't need to worry about that. So let's get started on that. I hope the logic behind why Ackermann steering is used is clear. If it's not, let me know. I'll give a more in-depth explanation in the comments if you'd like, with some sources and stuff that explain it more in depth. But like I said, it's basically a pretty simple logical explanation that if this wheel had the same angle as this wheel, that the turning radius would obviously be off. So that's why the car would start slipping in the left wheel, or if we're turning right, in the right wheel, which would cause understeer, or even worse, you would just not steer at all, which is awful. So yeah, let's go into Unity, and we have our car here, which of course still works. It still has the suspension on it. Now, I was actually in my previous lesson, I talked about the F button. If you press it twice in the old Unity, it would actually start following the model. But as you can see, the camera is static, and right now, if I just I can keep pressing it, but it doesn't do anything. It is not a bug actually, which is something that that a friend of mine who works with Unity bugs and stuff like that with bug fixes told me about after testing it himself. It's now Shift F, and as you can see right now, the camera follows it perfectly. Yay! So that's something for you to know as well. If you want to keep track of your model inside the scene view, Shift F is for focusing. It's not double F anymore. All right, so we have our script wheel, but the calculations that we want to do is actually better to keep in one script, because if you remember, this script wheel is actually copied 4 times. We have four wheels, so 4 times the script basically. So let's create a new script and just call it car controller, because this is basically where we'll put in car data, so wheelbase specs, the gear ratios eventually, the torque curve of the engine, stuff like that. This is just something that will keep the main car specs in its variables. And I was told I can create a template for this, but I have no idea how to do that yet. So possibly that will be fixed in this in the future. Oh shit! Sorry. Possibly that will be fixed in the future, but at the moment I have to do it manually. And let's create a header, because I love organizing things. And just call it car specs. Now we know we need the wheelbase, so public float wheelbase in meters. Public float rear track in meters, public float turn radius in meters. There we go. And that is it. So we need the wheelbase, turn radius, rear track, and of course steer input, but that's something that we'll have to set up with the input manager. For now, I think we can actually, let's just do it like this, create another header, inputs. You don't have to do the header things, by the way, if you don't want. It's just, I personally find it really nice to have that, organized. Let's call it steer input. And lastly, what I do want to do, and that is something that I did not mention in the example drawing, but also maybe I can zoom in a bit because I was told that would be better. So let's try that. I don't know if this this will work for you, but let me know if it was fine before. But yeah, what I did not talk about is that, of course, this steering angle that we're going to create needs to be applied to the front wheels, because the front wheels are going to perform the actual steering angle calculation. While in here we only do the setup. Basically, we get the Ackermann angle for both the left and right wheel, and then we send that information to the wheels. And then in the wheel script itself, we can determine, okay, these are front wheels or rear wheels. We can do that via a Boolean type, but I'll show that in a little bit. But the way we can do this really easily is just get the script wheel and make it an array and call it wheel. There we go. We don't need the start function for now. And in the update, we just need to know one thing, which is the steer input. If you're bigger than 0, so is turning right. Let's put an opening bracket there. Else, if steer input is smaller than 0, opening bracket, is turning left. And otherwise, if the steer input is 0, because if it's above 0 or less than 0, obviously if the last option in this if-else statement is just else, that can only mean if it's perfectly 0. So in this case, this one is quite easy. And I want to create 2 Ackermann floats. Ackermann angle left, private float Ackermann angle right, because obviously we need to keep track of which wheel basically is affected by this. So in this case, Ackermann angle left should only obviously affect the left wheel, and Ackermann angle right the right wheel. Well, there we go. Because I am really bad with that, keeping it on one line. Lastly, we need, of course, to know what the input is. Input get axis horizontal should be fine. So this will just be left right on the keyboard or your controller. We could change this later. For now, this will be fine. And now we come to the actual meat of the calculation. So if you remember, we have the calculation right up here. So Ackermann angle left equals mathf.rad2deg times mathf.atan. And we need to do the wheelbase, open bracket, because this needs to be one calculation, and plus in math is later than multiplying and dividing. So turn radius plus the rear track in meters. So rear track divided by 2. There we go. And we need one more closing bracket because that's the mathf.atan times steer input. So that should be correct. There we go. And then we just copy it, call this right, and make this a minus. And now we can easily copy paste this and just turn the minus and plus around. And lastly, make it 0, because obviously if there's no steer input, both the angles should be 0 as well. Right, okay, so this is the entire calculation. We don't need the Photoshop now. Let's zoom out a little bit. There we go. Now this is not going to do anything. We could make this public so I can show you after we filled this in. Like I said, we can get this information online if you just search for Supra wheelbase, for instance. As you can see, it's 2.629. And in this case, it's in millimeters, so it's 2,629, but in from millimeter to meter is divided by 1,000, so it's 2.6269. So let's go to Supra and apply the car controller. 2.269 or 629, what was it? My brain, no. 629, I got it correct, there we go. All right, I wonder if it's actually on the wiki. I doubt that the rear track information is on the wiki. So we have to wait, like I said in the previous episode, that is 1410 or 1510, depending on which version you have. Wheelbase, oh, in this case the wheelbase is a little bit bigger, 2.550. I guess there are different versions of the Supra, and in this case we have the 4th generation, the MK4, so it makes sense to actually use that information. All right, so we can't find the rear track there. Let's see if we can after getting the turn radius, because turn radius is probably easier. Turn radius. Otherwise it will probably be referred to as turn circle. Yes. Is this the Toyota Supra from nowadays though? Because this is probably this version. It doesn't have any information there. Right, you know what? I'm just going to use this because in the end we can always adjust it if necessary. And I don't want to hold you up. At least I just want to show you how you can find out the information. We probably could be like MK4 and then turn circle if we want to be really to the point of finding information about it. Prices, there we go. Here's the information about it. So a lot of information actually. That's pretty cool. I do not see turn radius, so turning circle meters 10.8. So it's actually exactly the same. That's great. Does this page also have track front rear? It does. Oh, this is a great website. All right, awesome. 1.525. Awesome. Okay, let's click play now. And now we should, as you can see, have an Ackermann, like I'm currently pressing the right input. As you can see, the steer input is 1, and if I press left, it's -1. So if I press 1 to the right, the Ackermann angle to the left wheel is 12.4, and the Ackermann angle to the right is 14.2. So as you can see, the right wheel, in this case, because we're turning right, is having a bigger angle than the left wheel. It's not by a lot, to be fair, but in this case, this is actually how the Ackermann steering function works. And on the left, as you can see, now the Ackermann angle right is 12.4, and the Ackermann angle left is 14.2. So the values are correct on both sides, and they actually flip around. So that is really cool. There we go. So now we have the setup, and now we need to apply it to these 4, or well, to these 2, I should say, because these 2 obviously shouldn't steer unless you want to make some really weird car. And in that case, you would actually have to calculate the rear and rear left and rear right wheels the opposite direction, because obviously otherwise this wheel is going to, for instance, to the right. So we're steering steering that way, so to the left actually, sorry. So if we're steering to the left and this wheel is also doing it, we're actually going to drive really weirdly like a crab almost. So in that case, if you want to do really wacky stuff, you would have to calculate that this wheel turns outwards if this one goes inwards. But I assume that you're here for actual car mechanics, like not weird stuff. So let's try and work on that. And for that, we need actually script wheel once more and give it 4 public bools. Public bool wheel front left, wheel front right, rear left, rear right. And now what we can do is on wheel FL, we can say your front left, your front right, your rear left, and your rear right, which is really handy because in this case we can also choose, for instance, if later in the episodes we want four-wheel drive or front wheel drive or rear wheel drive, and we can use these booleans to decide which wheels get traction in that case. So that is also really handy to have those set up already. All right. Now, what we need to do is create a void update, because we're going to change the rotation, and you don't want to do that in fixed update because that should pretty much exclusively be used for physics calculations, and this is not a physics calculation. So in here, we want to send our information to the wheels, basically. So for each script wheel W in wheels, and now we can say if W dot wheel front left, set the Ackermann angle left, or no, sorry, that is not correct. I actually forgot to add one more thing here, and it's good that you reminded me of that, guys. That's really helpful. Thank you. Wheel public float steer angle. There we go. W dot steer angle equals Ackermann angle left. There we go. If W dot wheel front right, W dot steer angle equals Ackermann angle right. And that's it. Now we actually are sending the information. So this script, this car controller script, is now done. For now anyways, because we're sending this information to this script. Based on the information in here, we are now going to tell the rotation axis of this wheel front right and wheel front left to turn based on the wheel, based on the steer angle. All right, so let's go to transform.local rotation equals, and now I do need to look really quickly at my own calculations because otherwise I might mess it up, because this always is painful. And that local rotation is a quaternion.euler transform.local rotation.x transform.local rotation.y plus the steer angle, and then local rotation, .z. So basically what we're doing now is adding the steer angle to the existing transform.local rotation. So if the local rotation is already on an angle, then this steer angle will just be added to it, basically. And since the steer angle gets its information from this piece, so the Ackermann angle left, Ackermann angle right, that is actually multiplied by the steer input, it will be dependent on how much we press the button. Now, in terms of the keys itself, obviously it will be less manageable. You can't really give it like half a push or 25% of a push? Well, on a controller you could. That is why personally I prefer racing games with a controller, or even a wheel. That's even better. But for this tutorial, we're not going to look into wheels just yet, if we even get to that at one point. But yeah, controller is the best, because with the controller you can actually move the thumbstick on the left like only 25%, just to see if that gives you different angles. But yeah, let's see what this does. Play. And since we have this one selected, we should see, if I press the right, we should see that it moves, which it doesn't seem to do right now. Am I getting crazy? Or have I not set up the input yet? That is possible. Axes. Horizontal. Yes, you are set up. Okay. Okay. So now it's time to debug, because from what I can tell, this should work. We ask if the steer input is bigger than 0, then we set it to this, otherwise we set it to that, and otherwise it's 0. But we knew that that worked because we already checked here. If we press this, then it will actually go up and down. So it's not the fault in this script. So possibly it's the fault in here. All right, guys, welcome back to to the training. Now it is super embarrassing. But this is something that yeah, you'll probably do a lot wrong as well from time to time. We obviously didn't set the wheels themselves, so the computer doesn't know how many wheels there are, to which wheels we're trying to send information. So the calculation actually is perfect. The code is nothing wrong. I tried this, but let me just remove that because it literally shouldn't matter. So yeah, the code is perfect. We just didn't establish which wheels we're trying to send information to. So let's do that instantly. Just add 4 wheels, and we want to add that one, that one, that one, and that one. And now, if we go here, there we go. Now we can actually see the rotation. And we actually see it on the thing as well, and we see it here in the steer angle. So if we turn right, the left wheel has 12.4 as its steer angle, and if we turn left, it has minus 14.2 as its steer angle. And for the wheel right, obviously, it's exactly the same. So, like I said, this was embarrassing, but I try to keep mistakes in because I want you to learn from my mistakes as well. And yeah, if I would just have to, re-record the entire thing, it would be less authentic, I feel. And yeah, if you spotted this issue before I did, props to you. Like that means that you're actually understanding what we're trying to do here. So that's good. So yeah, we got the steer angle, but one issue that I found, if we just apply it straight to this, is that once we let go of the button, this is fine. It goes between the two just fine. But if we press left or right while we're fully left or right, you can see there's a snap in there. And personally, it isn't an issue per se, but it triggers me. Like I want there to be a smooth motion between the two, especially because a wheel doesn't just snap from one end to the other. There's a steering time, and obviously the faster you go, the easier it is to move the wheel left and right. But yeah, the snapping itself is what has to go, in my opinion. So I'm gonna do that as well, really easily. Private float wheel angle. This is a new float value that we're actually going to use to keep track of the current steering angle of the wheel itself, and then we're going to lerp basically to what it needs to be. So if it's at 0 and we want it to be 12, for instance, 12.4, then it will lerp slowly with however fast we want it to be from that 0 to the 12. If we then press left, it's going to be at 12, and it's going to minus 14, but it's going to lerp from 12 to minus 14 basically, instead of snap from 12 to minus 14 instantly, which is just not what we want. So this calculation is fine. We could simplify this a lot. We could just say factor 3 Math.op times steer angle. That works as well, as you will see here. See, nothing changed. So it's just a little code cleanup, basically. It doesn't change anything. But we want to replace the steer angle with wheel angle. And obviously wheel angle has currently no setup to it, so it's not going to do anything. So we want to address wheel angle here. And we want to say, in this case, mathf.lerp. And we want to keep track of wheel angle. And we want to get to the steer angle in the time it takes. So this is a value we need to create as well, times delta time. There we go. Now the reason we use times delta time is because we do want it to be the same on every system. We don't want a computer with really fast processing power to steer faster than another computer that has a really slow processor, for instance, or graphics card. So lastly, we need a steer time, and we can add that here to these two, and we just say maybe 8. I think I had that in one of my other projects, and as you can see now, no more snapping. It is perfectly smooth. So it's not a lot of lines that I taught you today. It's just that we needed to figure out the Ackermann angle. So in this case, it is multiple lines, but it's basically the same line every time. It's just turned around the plus and the minus. Then we needed to apply it to the steer angle of the actual wheel. And in this case, only the front left and front right wheel. And this is not something that you want to do, but if you wanted to do it for fun with the rear wheels, rear wheel left and rear wheel right, then you could actually put a minus in front of this, probably. I'm not sure if that works, but that would probably help with setting the orientation differently. I'm actually curious if that works. Now that I brought it up, I kind of want to know if it works, yes or no, because I literally just thought of this on the spot. Like, that would be a fun experiment. All right, so if I press right on this, oh wow, it actually doesn't rotate. I broke it. I broke it. Does it rotate on the front? It does. Okay, that is weird. Ain't nothing like things going wrong, am I right? Oh my god, that is funny. No, it should work. We don't do anything special here. So okay. Well, it was just something fun anyway. I really don't want to waste your time by trying to figure out why that doesn't work. I was just curious if I could get it to work for you and just show you how you could probably do like a really wacky car, but it should work with that logic, but there's probably something that I missed or something, but you could probably work with that. Basically, you want to turn around the sinus of the sign of this wheel opposite of this wheel. So if you turn left here, you basically want to turn right on this wheel to create still the turning circle. Otherwise you have a car that either moves that way or that way instead of actually in a circle. So that is basically the logic behind that. But yeah, we have the front left and front right wheel ticked here. So we know that those two will actually get the information from the steer angle that we applied here. Then lastly, we created steer angle and steer time and wheel angle. So it's 3 variables, and we applied that here. So wheel angle is used to keep track of the current wheel angle. The steer angle is the information we get from the car controller, so how much we need to go left or right. And the steer time is how long it takes to get there. So if we set this to, let's say 28, it's going to be really slow, or well, it should be. Or really fast. Opposite, sorry. If we set it to 1, it's going to be really slow. Yeah, there we go. So let's set this to maybe 10. I don't know. We can probably in the future play with the steer time based on the current car speed, because obviously if you're standing still, you need to have more force applied to the wheels to rotate them. But yeah, I don't think that might be within the scope of this tutorial. Anyways, I hope you enjoyed. I'm sorry for the mistake that I made with not putting in the wheels in the actual array. But yeah, like I said, learn from my mistakes. I'm gonna probably keep making 1 or 2 mistakes per tutorial if it keeps going like this. Use your resource as well. So in this case, the information about the wheelbase, rear track, turn radius, etc. was just something I found through Google. So you can do that the same for your own car if you want to follow along. And yeah, that's it. This is how we can create the Ackermann angle for steering, and this is how we can help our car not flip around or not steer at all due to loss of friction or anything like that. So I hope you enjoyed, and I will see you next time. Bye!